This is a short video about a feature that I have included in the forthcoming QSX transceiver kit to help with aligning the bandpass filter. It's basically a built-in miniature spectrum analyzer with tracking generator which allows you to plot the filter characteristic on the screen. So I'm going to show you that next. The QCX transceiver, CW kit transceiver introduced last year, one of the most popular features commented on about this kit is the built-in test equipment features. So one of the features in that kit was the bandpass filter alignment tool. This is my QCX30 kit, and to get to the alignment tool I go into the menu like this. I scroll through to the alignment menu, then I scroll through to the item which is called BPF peaking. I press select. Now you can see the bar on the screen, and I would just adjust the trimmer capacitor to peak that bar. Later the same bar technique is used for the IQ balance and phasing adjustments. In the QSX transceiver we don't have these adjustments because it's a software defined radio and it's all done digitally. Bandpass filters are used to help attenuate out-of-band signals, such as from strong shortwave radio stations, which could interfere with the wanted signal in the radio's front end, creating intermodulation interference products. The bandpass filter on the QCX is a single trimmer capacitor, but the one on the QSX is the same design as the QRP Labs bandpass filter kit, shown here in this picture in a test fixture for a spectrum analyzer. So here is the spectrum analyzer. This is an expensive piece of equipment, and the only reason I have it is because it was already 20 years old when I bought it. Second hand, third hand, fourth hand, whatever hand. Here I'm sweeping the passband characteristic of the QRP Labs bandpass filter kit. This is a 40 meter version, and I'm going to show you the 40 meter QSX in a moment. And you can see that I can do things like change the start frequency. Here I'll change the start frequency of the sweep to 3 MHz and the end frequency of the sweep to 8 MHz. So you can zoom in, you can tune around with the cursor, you can make measurements and so on. So a very useful piece of equipment. Many people watching this video may have not encountered one. The double-tuned bandpass filter circuit is a little bit more tricky to align than the single-tuned version. The two resonator circuits both need to be tuned to the correct frequency, otherwise you can end up with a double hump with some attenuation between them in the middle, which is not really desirable and not getting the most out of the circuit. So a spectrum analyzer really helps to make this easy. And you can see as I turn the trimmer capacitors, you can see the filter shape changing there. It's particularly useful on the higher bands where you can quite easily get a much wider tuning range because the fixed capacitors in parallel with the trimmers are not so large. Now here in this 40 meter QSX you can see the same filter circuit here with the two trimmer capacitors and the two toroids. That's the 40 meter bandpass filter that is going to be tuned. Here we are with the front panel of the 40 meter QSX prototype, and the menu structure is quite similar to the QCX, at least superficially so. So you'll see that I can press the left button to go into the menu and scroll through to find the setup menu. We now have sub-menus within the menu system, and one of these is the alignment menu. The second item on here is the bandpass filter alignment, and you'll see what happens when I press it. What we've got here now on the display is a miniature spectrum analyzer built into the QSX transceiver with a tracking generator sweeping the passband performance of the 40 meter bandpass filter. Now the QSX transceiver has a low-cost HD44780 alphanumeric LCD module as its display. Now these are used for displaying text and characters, not for displaying graphics, but they do have 8 custom definable characters where you can define your own pixel pattern as you wish. So what I've done here is I've used those 8 characters to create a display section in the middle here which is 20 pixels wide and 16 pixels high and creates a miniature spectrum analyzer display. You can imagine it really as 23 pixels wide and 17 pixels high once you take into account the non-displayable graticule divisions, which are the gaps between rows and character columns in the display module. So some explanation about what you're seeing here. On the bottom right hand corner, this is the number of megahertz per division of the horizontal axis of the spectrum analyzer. So we have 4 different divisions and each one is worth 1 megahertz in this example. It means the sweep from left to right is 4 megahertz. On the top right, this is the number of decibels per vertical division. We have 2 vertical divisions, each one is 18 dB. That means the height of the display from top to bottom is 36 decibels. As you play around with the spectrum analyzer, the height adjusts automatically so that the picture always fits on the full screen. On the top left, this is the decibel measurement of the peak of the bandpass filter characteristic. It's entirely arbitrary at the moment. Hopefully in the future I may be able to make that show an insertion loss, but even if not, at least it gives you a nice numeric way of peaking the filter and seeing how high you can get that peak. At the bottom left, this is the center frequency, 7 MHz, so that shows the center column here in the display. The display sweep is updated about 2.5 times per second. You can also use the left and the right rotary encoder knobs. So the right rotary encoder adjusts the center frequency. So you can see as I turn it, the center frequency here changes to 8 MHz, and so that means 8 MHz is this line here. So the bandpass filter characteristic has shifted to the left. And I can go back and I can go the other way as well, like that. Okay. Then on the left rotary encoder button, we can zoom in. So if I turn it left, it actually reduces the sweep. So you can see now this has become 500 kHz per division. The display adjusts itself automatically, the height of the display, so that's why the decibels per vertical division are going down up here. So you can see effectively you're zooming in to get the fine details of the peak. You can actually zoom in all the way down to 1 kHz, but there's not really very much point to that. A more suitable value is something like 200 kHz or 500 kHz per division. You can, even if you want, you can zoom out to as much as 50 MHz. Again, not much point to that. But for example, 10 MHz, we've got a possibility of a 40 MHz sweep. So you can see the 7 MHz peak up here on the left, and you can see how the rest of the filter characteristic looks. It's never going to be perfect because you're looking at various leakages through the circuit and so on, but it's a good enough indication to be able to align the filter very nicely and give you an idea of the characteristic. So now if I bring that back in to more sensible values, another feature that we have on this display, you can see this horizontal line of pixels along the bottom row. This actually shows the ham band. So if one of the frequency samples is within the 40 meter amateur radio band, then these pixels along the bottom row will be colored. So it shows 7.0 MHz on the left here and 7.3 MHz on the right. So you can make sure that your filter is nicely tuned in the middle. Now if I go in and I start messing around with the trimmer capacitors, you can see that it starts to move off to one side. Another nice feature I've got in here is a measurement of the 3 dB bandwidth. So if I press the left button, this top left field of the display toggles from the peak dB reading to a bandwidth reading. So that 0.65 MHz is the 3 dB bandwidth measured of this filter, and it's quite a normal kind of range for the 40 meter filter design that we've got here, and quite suitable. It covers the whole 40 meter band without significant attenuation at the edges. So there you have it. It's a very nice and unique tool to have built into a radio transceiver to help align its filters, and goes one step further than just seeing an amplitude measurement, being able to actually plot the filter response is really interesting. It will be also quite educational for many people who haven't got access to a spectrum analyzer and who perhaps haven't used one before, to be able to see how they behave. Essentially, it behaves pretty much like a real spectrum analyzer, of course with a very limited display and limited functionality, but good enough to sweep through the filter performance with its tracking generator. So there we go. Now all I have to do is finish the rest of this thing.